Good evening, everyone. My name is Vikki Spruill, and I am the president and CEO at the New England Aquarium. I began my tenure here at the beginning of August, and I'm truly honored to be with you here this evening. It's really a dream come true for me to return to my roots in ocean conservation after leading the Council on Foundations for the past 6 years in Washington, D.C., and prior to that, Ocean Conservancy. I'm very excited to have a chance to activate my vision for the aquarium, which is to build on our very rich 50-year history of scientific research, inspiration, and education by strengthening our work in conservation, policy, and advocacy. So I want to thank you all for coming here tonight and for your interest in learning more about what we all can do to protect our blue planet. And I'm honored that we're in this partnership with the Massachusetts Institute of Technology's Lorenz Center. It's a real honor to be here. I don't need to tell this crowd that our oceans are in trouble. Many of you probably read the report, actually just earlier this week, issued on Monday by the United Nations Intergovernmental Panel on Climate Change. It was pretty depressing. It's a dire report. In only 20 years, among other catastrophes, we're likely to see global food shortages, worsening air quality, and a massive bleaching of the world's coral reefs due to climate change. What you may not know is how important coral reefs are to people. They generate about $30 billion annually and sustain about $1 billion people through coastal protections and food security and income. And they're critical to the health of our oceans. Earth's coral reefs support more species per unit than any other marine environment, including more than 4,000 species of fishes and hundreds of other marine wildlife. And that's only one impact climate change is having on our oceans. So that UN report is an urgent call to action. We must reduce global greenhouse gases now, actually right now, or the oceans, all of the Earth really, will face irreversible consequences. And so that's really why we do what we do here at the aquarium, educating about human impacts on our oceans. And through our science and research, we learn about how marine life adapts so that we can help those animals and ourselves to better adapt. We're using the Gulf of Maine in our backyard, which is warming faster than 99% of all bodies of water globally, and we're using that as a living lab. And through programs like the Marine Conservation Action Fund, we're able to apply our science to vulnerable ecosystems across the planet. All of the species we're studying at the New England Aquarium are being affected by climate change, whether it's the iconic Atlantic cod, the critically endangered North Atlantic right whale, or the sand tiger sharks that are now showing up in Boston Harbor. In order for us to help solve the challenges that come with climate change, we have to better understand what's happening. And that's why it's so important to be doing the fundamental research that we're doing at the aquarium. You may have heard about the efforts of the aquarium's Anderson Cabot Center right whale research team, that's a mouthful, on NPR's Morning Edition just on Monday. Since 1980, aquarium researchers have been studying the critically endangered North Atlantic right whale back when it had a population of about 300. Today, it numbers under 450 as it faces threats from fishing gear entanglements, from ship strikes, and yes, from climate change. It's believed that climate change is affecting right whale habitat and that their feeding grounds are forcing them to find plankton, affecting the feeding grounds, forcing them to find plankton farther afield. Knowing this, our researchers are using a science-based strategy to advocate for better protections as they've advocated for these beautiful animals for nearly 40 years. Past successes include developing vessel speed restrictions and changing shipping lanes, which reduced right whale deaths. But it's not only the whales in our backyard we seek to protect. The oceans are global, and so are we, and we're using our decades of research to determine best practices and help protect species and ecosystems around the world. So that UN report states human influence on climate systems is clear. Yes, humans are responsible for global warming, but that means we're also the solution together. You, me, all of us, we can stop this in the long term and in the present. And it's why our partnership with MIT is so important and why your being here is vital. Together, we represent hope for our ocean planet. And we're so proud to partner with the Lorenz Center at MIT. The Lorenz Center is in the Department of Earth, Atmospheric and Planetary Sciences at MIT. It's named in honor of the late Dr. Edward Lorenz, one of MIT's most distinguished faculty members, who pioneered chaos theory, and I'm sure many of you have heard about the butterfly effect. The Lorenz Center brings the best scientific minds together to study our climate and how it works, and they study the interdependence of life and climate and how life evolved on Earth. This is a very special planet. I like to call it an ocean planet, the only planet that we're aware of that sustains life as we know it. But life is also fragile. We've experienced mass extinctions in the past, and think about that. We've seen events in Earth's history that wiped out 96% of marine species and 70% of land species on the planet. Could that happen again? Has it already happened on other planets? To study the coevolution of Earth and life, we must also learn not just from our own planet, but from our neighbors in the solar system. Is there life out there? Did Mars once host life? Certainly, scientists say there was once water on Mars, and maybe there still is. And tonight, we're going to find out all about the search for ancient life on Mars. The Lorenz Center, MIT, and the Aquarium share a passion for science and discovery, and we hope through public events like this to inspire your curiosity, as well as your respect and love for the Earth, so that we can act to protect it in an era of climate and global change. I want to thank John Carlson for endowing this special lecture series. John is in the audience tonight. Thank you, John. And Daniel Rothman, Professor of Geophysics at MIT and co-director of the Lorenz Center, for bringing the annual John Carlson Lecture to the New England Aquarium. Dan will now introduce our speaker, Dr. John Grotzinger, and his presentation, Searching for Ancient Life on Mars. Thank you.
Thanks, Vikki, and thanks to the Aquarium for hosting the 8th Annual John Carlson Lecture. Together with my colleague Kerry Emanuel, who's on sabbatical and therefore not here, I co-founded MIT's Lorenz Center. The Lorenz Center is devoted to learning how climate works. One of the ways to do that is to look broadly beyond our own planet. Thus, it is a pleasure to introduce this year's Carlson lecturer, John Grotzinger, who will tell us tonight about evidence for past climates on Mars. John is a geologist. His interests are wide, but many of them focus on sedimentary rocks. To John, ancient sediments are not just rocks. They are recorders of history extending back billions of years. This record not only contains fossils, but also chemical traces of the history of the coevolution of life in the environment. John is one of the world's leading interpreters of that history. His work has led to a fundamental reappraisal of the earliest signs of microbial life, significant revisions of the timeline of early animal evolution, and a greatly increased understanding of the ways in which major events in the evolution of life are coupled to major episodes of environmental change. In recent years, John's interest shifted to Mars. In his 8 years as chief scientist for NASA's Mars Curiosity rover mission, and in his work on other Mars missions, John has used his understanding of geological processes to unravel the history of the Martian environment from its own rock record. Could the ancient Martian climate have supported life? Such questions have occupied John's attention for the last decade. Before moving to Caltech and Mars, John was our colleague at MIT for 18 years. Those of us who have worked with him, and there are many, have had our lives enriched by John's enthusiasm for new scientific ideas. We're therefore delighted to have him here at the Aquarium this evening, where he can share his latest insights more widely before the general public as he tells us about searching for ancient life on Mars. Let's welcome John Grotzinger.
Great. Thank you very much, Dan. It's really a pleasure to be here, and thank you all for coming out on a rainy night. I see it's pretty full, and I guess I'm grateful that the Red Sox won the other night. Didn't have to go into another game. What I'd like to do is to give you a very broad perspective of how we as scientists go about exploring a planet like Mars, with the rather audacious hypothesis that there could have been once life there. We don't know that. We arrive at that conclusion slowly, that it is a worthwhile hypothesis to explore. So I'm going to try to give you the basis for how we do that. I'm going to tell a story about the evolution of a particular spot on Mars that we know as Gale Crater. And it has a mountain in the middle that you can see here, you've been looking at, that we call Mount Sharp, after Robert Sharp, who was one of the pioneers of planetary geology. This mountain is 5 kilometers high, and the crater itself is 140 kilometers in diameter. That's about the size of the big island of Hawaii. And right now, the Curiosity rover that's been operating for 6 years on Mars is just emerging from the shadows down here and exploring this ridge that you see right here. In the next couple years, Curiosity will make her way up this valley to the contact between these dark rocks and these light rocks, having gone 25 kilometers and ascending almost a kilometer in elevation. So this is a classic mission of exploration, where a team of scientists heads out into the unknown. Our vehicle is not a ship, but a rover on Mars. And with it, we have some ideas that we're trying to explore about what the basis for life might have been on Mars. It is a big team, a lot of people to give credit to. These are 250 scientists and engineers that were required to operate the rover every day in the first 6 months of the mission, when we were first getting to know Curiosity. When you build a spacecraft, you don't know exactly how it's going to operate until you kick the tires a bit. The team is necessarily smaller now, but there are other scientists who aren't in this picture that look at the data and help us make decisions about what to do next with the rover. So they represent 13 different countries. There are 10 scientific instruments that were built by 9 principal investigators, and the total team size is about 550 scientists. So without them, it wouldn't be possible for me to be here. So Dan mentioned my interest in history of the Earth and now the history of Mars. And so I wanted to give you some exposure to how we go about exploring this history as scientists. So we're interested in water on Mars because without evidence for water, you have no basis for life as we know it. And landscape evolution turns out to be important because how that mountain formed and what's in that mountain represents a record that could preserve evidence for life and past climatic conditions that are important for life. And all of that is embedded in what we call a stratigraphic record, which is just a series of layered rocks, much like you would see in the Grand Canyon. So I'll begin this story by talking a little bit about Percival Lowell, who was an amateur astronomer around the turn of the last century, who expanded on an idea first fronted by Giovanni Schiaparelli, that there are canals on Mars. And Lowell became infatuated with this idea and invested and built an observatory in Flagstaff, Arizona. This was the first time that someone had ever built an observatory in the middle of nowhere to get beyond urban influences. But you can see his idea here that he imagined that there were these canals. And he hypothesized that there was a desperate race of people who were on the verge of extinction, and they were trying to funnel the water from the polar ice caps to where they lived in order to stay alive on a planet that was undergoing inexorable decline of all its climatic conditions. So if that sounds familiar to your introduction of what we're doing on Earth, you're not alone. Okay, so this fueled the public's imagination, and it kicked off NASA's exploration of the solar system. Planetary geology was born. A little bit later, the Lunar Apollo astronaut program was started. And when the first missions went by Mars, they were called flybys. There's basically three ways that you can explore a planet. You send a spacecraft right by it, you get a couple of glimpses, and then it goes on to the next planet. Or you go into orbit around the planet where you can observe it over and over again. And then when you feel like there's something really worthwhile, then you can land on it with a lander or a rover or something like that. So the first mission that was successful and made it to Mars was Mariner 4 in 1965. And just like that, all of Lowell's canals went away. And it was depressing. And so basically people looked at this image and said, this doesn't look much different than the moon. And we know the moon doesn't look very attractive as a habitable environment. So Mars also looks pretty bad. And then there was about a decade of exploration that culminated in the first landers to arrive in Mars, the Viking landers. There were two of them. There were two orbiters and two landers. And these landers were equipped with scientific instruments that were designed to look for life. So they could tell if there were microorganisms or something living in the soil that were respiring and exchanging gases. They could detect that. Those experiments were failures. You look at this surface, it looks lifeless. This is as exciting as it got. On a few days a year, there would actually be frost. Mars has almost no atmosphere, but the temperatures get down to below 100 degrees centigrade, and what little water vapors in the atmosphere occasionally will condense and precipitate out as ice on the rocks, and then it goes away. No more water. So it looked bad. Congress canceled the budget for further exploration of Mars. And we didn't do anything for about 20 years until the science community was able to study the planet enough on the existing data to reach the conclusion that while the modern planet was uninhabitable, and we still think it is, you might have to go deep within Mars to find evidence of modern life, maybe the ancient history might have been viable, and life could have evolved and then become extinct. So that's where we are now. So when we talk about searching for life on Mars, we're not talking about Lowell's vanished race. We're talking about microorganisms like these guys here, simple one-celled microorganisms that we know have existed on Earth for the last 3.5 billion years, a long time. They originated, they adapted, they evolved, and they didn't change very much until you had the emergence of animals just 500 million years ago. But for basically 3 billion years, the planet was pretty much alone with microbes. So the question is, could Mars have done something similar? But then we know that the climate undergoes catastrophic deterioration, and we lose the atmosphere, and the surface of Mars becomes uninhabitable. These microbes could have gone extinct. So this is a rational hypothesis that the science community can pose. So what makes a place habitable to a microorganism? Well, the first thing you need is you just got to have water. So the first question you ask of any ancient planetary surface that you want to explore is, was there once evidence for water there? And then, if you're able to answer that with a yes, then you go to the next step, which are, can you find the key ingredients for life? Are the nutrients available in a form that if a microbe was there, they could actually utilize these to metabolize and respire? So those are the key ingredients. So the first rovers that were sent to Mars were designed to look simply for the presence of water, and I'll talk more about that in a minute. So they saw that, and then on a decadal timescale, Congress then made money available to build the Curiosity rover that I was involved with. And there we answer the next two things that you see here. So we want to find a place where we're going to discover ancient water, meaning bound up in rocks and minerals, really quickly, and then get on with the business of what was the environment like in more detail, and did you have the chemical ingredients that were necessary for life? So our mission is a chemistry mission. Okay, so let me go back to the 60s with Mariner 9. So with Mariner 4, you get the first glimpses of Mars, but you're only mapping a small postage stamp. Then with Mariner 9, you get a more capable set of cameras. You eventually get spacecrafts that go into orbit and they start mapping. And suddenly you see, this is not so bad as those first pictures looked. Because now we can look up and we see these channels. And people wonder what carved those channels. And all the science community agreed right away, some kind of liquid. But then the argument began, because it doesn't have to be water. It could be liquid CO2. It could be liquid nitrogen. It's super cold on Mars. Maybe it was even colder in the past. And so, but something flowed across the surface and made these channels. And then some people said, well, maybe if we build a better telescope, they will go away. It's an artifact. So what you see down in the bottom is what happens a decade later with Viking, where they're still there, but they're even in more detail at higher resolution. So what we can see in this picture, and we now know that it was water that carved this. I won't go into that, but if you want to ask afterward, we can talk about it a little bit. That you see evidence of water flowing across the surface and carving channels, just like we see on Earth. And the prediction of that is that all the mass that's being removed by this erosion has got to go downstream somewhere. And so the prediction is, if this cycle closes on itself, you'll see the place where all the sediment got transported to. But it took decades till we got an even better camera in orbit around Mars. And then with this, we see with Mars Global Surveyor Orbiter, the first delta. And this really looks Earth-like. And so I think with this discovery, NASA then went into high gear, because this tells you two things. One is, it just reinforces the idea that water was flowing across Mars. But a delta really only forms where there is a body of standing water. Otherwise, the river just flows down into a depression, and the water sieves through the soil, and you get dryness. But here, the delta means that there was a body of standing water. Well, that's really important, because that changes your view of the history of climate on Mars. Because if you have a body of standing water, it has to be in equilibrium with the atmosphere. If you have the atmosphere that you have today, and you flowed water across the surface, it would be boiling as it flowed, and it would never accumulate as a body of standing water. So this tells us that at least for some brief period of time, if you want to be conservative, or maybe even a long period of time, water was there, the atmosphere was denser, this is a good thing for life. So, but that gave us then the license to start building more sophisticated rovers. So you can do more of this analysis and now go global, because you don't want to get faked out by just one of something. So here's a map where the science community just simply plotted yellow dots wherever they saw something that looked like erosion in rock by water. And then after I first arrived at Caltech, this was a map that my group made where we looked down for evidence of deltas where the sediments were accumulating that were derived by erosion of that bedrock by the water. And so what you can see is that the planet has this latitudinal zone of erosion by water and deposition in water, and they balance each other. Okay, we're going to go back again and now look at the next major concept that I need to introduce here, and that is one of a stratigraphic record. So we go back to Viking data, and this is the wall of a really big canyon called Valles Marineris. It's 5 miles deep. It's the biggest canyon in the solar system. And there are major avalanche piles that go down for kilometers down the sides of the canyon. And they're rooted in the top here, where there seems to be a darker gray material that is sloughing down slope onto something that's lighter toned. So what this tells you is that the planet is layered in some way, so that you have an upper darker layer and a lower whiter layer. But nobody knew what those things were. And there were lots of hypotheses. Could be volcanic rocks, could be sedimentary rocks. Maybe it's kind of rocks that form when impacts hit the ground and send debris flying, and then it falls down, and that makes a layer. So it wasn't until 2004 when the Opportunity rover, oh my goodness, God, Microsoft. All right. Wow, that was dramatic. don't want more fonts. That's not a good sign either. All right. Yeah, Apple. It used to be a great company. Hey, all right. I think we're still winning. Okay, great. So when the Opportunity rover landed, we actually see a really good stratigraphic record. And what I mean by that is that you see bedrock, and it's all layered, one layer on top of the other. And the cool thing about this image is that you see layers that are parallel to the white lines I've drawn. But beneath this lower white line, you see layers that are dipping at an angle. So we can start to do stratigraphy by dividing these layers up into a lower unit, a middle unit, and an upper unit. And that's like basic geology 101. But this is important because these are the kind of rocks that on Earth fossil records are preserved in. Sedimentary rocks where you can start at the bottom and see one kind of fossil and go up later and see other kind of fossil. So when you look at these layers, it's like reading a book. You start at the bottom and you get to the first chapter and you get to the top and you get the last chapter. So what was so exciting about this is that about 200 years earlier, you have James Hutton, who is sort of the father of modern geology, sailing around Scotland and discovering a place called Sicker Point. And this was the first time that I think humans were able to fathom what scientists call deep time. And when you look at this, you know, their minds become giddy because they're basically figuring out that there's an unimaginable amount of time that's represented by the deposition of these rocks, which were once horizontal, and then they got tilted, and then they got eroded away. And then this student has his hand parallel to these layers, which are not horizontal, they're also dipping. And what they were digging into here was appreciating what we now call mountain building, where you have older rocks that are involved in plate tectonic collisions. They go up, they get eroded, the surface of the land comes down again, and then new rocks are deposited, and the cycle goes on and on. So what we were seeing on Mars is something similar to this. But the difference is it didn't amount to mountain building. It amounts to environmental change, climate change. And what we see here, and the way we interpret this record, is that these dipping layers on ancient Mars, and we're talking like 3.6 billion years ago, are similar to these layers that we see in modern deserts today, where you can dig a trench and you find sediments that are tilted at an angle because they were deposited in ancient sand dunes. So sand dunes have this shape, and when they migrate along, the sand grains slide down the front of the face, just like you see if you go out to Truro. And as the dune moves along, it leaves these tilted layers. And then after those tilted layers go by, then you get this lighter colored stuff up here, which is equivalent to these flat-lying layers, and that's where the water is. This is an ancient lake. It was a lake bed that was once wet, and then it got dry. So we can divine from this then that this is dry Mars and this is wet Mars, and climate is changing on Mars. But it tells us that water was standing, at least at times. So here's an analog from near the border between the Sultanate of Oman and Saudi Arabia. And these sand dunes are tall, some of the biggest in the world, hundreds of meters high. And then in between them, you have these interdune depressions that occasionally get wet. It happens rarely. It might happen once every 10 years. But when they get wet, there are microorganisms there, because the microorganisms are living down in the deeper subsurface where it's still wet all the time. And as soon as the water comes up to the surface, they're there. But the important thing is that they're living there in a place where that water will then evaporate and make salt. And the salt is a really good thing because it like hermetically seals the microbe and preserves it. And then if that can become rock record, you might find fossil microorganisms. So we were super excited about finding these kinds of rocks on Mars because it simply says keep looking. It's worth it to keep looking. Okay, now we're going to go global again. So in the meantime, our little rover is making this discovery of finding ancient salts deposited in an ancient lake. And at the same time, there's an orbiter that's mapping Mars, looking down for evidence of salts and clay minerals. And so there's a place, here's that big canyon I showed you a minute ago, where we saw the layers. But there's another one over here that looks like a big basin with channels running out of it. It looks like a place where there was once water. And there's a mountain over here, and now that's blown up over here. And so you can see this mountain. These are the sides of the canyon. And you look at this mountain, and you zoom in and you look at it, and it's layered. And the interesting thing about it is that the lower part, the bedding is not so well developed. The upper part, the bedding is really well developed. And it turns out that if we look down from orbit with a special kind of an instrument that I won't go into, we can tell what minerals are there. And so the lower part down here is a mineral called kieserite, which is like magnesium sulfate. You can think of it as Epsom salts. You go to the drugstore, you buy the salt, put your feet in it, soak a little bit. And then above it, we have something called gypsum, which is what plasterboard is made out of. That's calcium sulfate. And so what's incredible about this mountain is that it's telling us that we go from a time when water was precipitating magnesium sulfate to a time when water was precipitating calcium sulfate. And now we'd have to do the head scratching of trying to figure out what that mineral transition means. But in any version of that interpretation, there was water involved. And now we're talking about layers that are kilometers thick. That cannot be a flash in the pan. This must represent a longer period of time. Okay, so now let's go back to England. Okay, so 200 years ago, in 2015, we celebrated the bicentennial of the world's first geologic map. And William Smith was a surveyor who dug canals through England, and as a result of digging canals, he couldn't help but to look at the rocks that were there. And so as he looked at the rocks, he found out that they were distributed in a very systematic way. And so he abandoned his job, got a horse, and spent 10 years making this map. And if you read the notes that come along with this, he basically says, if you buy and use my map, it doesn't actually say that, but it does say that this map could be a guide to the productivity, the economic productivity of England, and lead to an industrial revolution. And needless to say, the gray layers are where the coal is, the yellow layers are what most buildings are made out of in Bristol, and so on and so forth. And they're just laid out here, and you just have to figure out what their geometry is. So he did that. And what he recognized is that as you go from Wales to the English Channel, you go from older layers that are tilted, they're all tilted, and the younger layers are over here. And there's one over here in green, and the word there says chalk, which is derived from the Greek word krita, that means chalk. And what's important about this is that he picked a name of a mineral to describe these rocks. And that will turn out to be important in a minute. So what Smith recognized as he dug these canals is that the rock types would often change. Sometimes you'd have a sandstone, then a shale, then a limestone, then a sandstone. And then you go to another different place, it goes from sandstone to limestone to shale. It looks different, but what he noticed was if you look at the fossils in there, there are patterns. And the fossils never change their sequence. So trilobites come first, and then ammonites are up here, and then you come over here, ammonites are at the bottom, and you wind up here with brachiopods up there. And so he recognized that there is passage of time that is being recorded by the succession of fossils. But it fell to his nephew, John Phillips, who apprenticed with him, to keep this work going. And what Phillips did was make the first geologic timescale. And it's really important that we talk about geologic timescales to understand how to explore for life on another planet. So what Phillips figured out is if you take all the rocks and all the fossils that are present in England, you have 3 periods. One down here called the Paleozoic, and one in the middle called Mesozoic, this time of dinosaurs. And then one up here called Cenozoic. And in between, there are boundaries that we now know are major extinctions. But he didn't know that those were extinctions at the time, and it didn't matter. He just proposed that this was a way to divine the deep time and understand that it was passing by. So what is a geologic timescale? We have to do this for just a minute. Geological timescale has two components. One is a relative component, and the other one is an absolute component. In the relative one, you just take something that's changing with time and put it in its proper order. And then with the absolute component, you take something which can be dated using the principle of radioactive decay, and then you calibrate your relative ordering. So on Earth, the way we do it is like Phillips started it. We take fossils, and then we have to wait till we discover radioactivity in the middle 1900s, and then we can use minerals like this to basically determine just how old the Earth really is, which was a great challenge in Victorian England. And on Mars, we don't know that we have any fossils yet, but we know that we've got minerals that have particular properties, and we can arrange these minerals in order, and then if we get lucky, we can take minerals that occur on Mars and date those, and we did that with the Curiosity rover. For the first time, we were able to date rocks without bringing them back to Earth. Okay, now this next slide, please don't try to read a single word. Just look at the colors. And notice at the bottom there is green, and then it goes into yellow and red, and then it winds up with brown. And then the other thing you need to notice, there are some names up here. This is Gale Crater, where Curiosity is. These are different places around Mars. And so this is us sort of bootstrapping our way into creating a global chronology based on minerals. And the greens mean there were clay minerals. These colors mean that there were sulfate minerals. And these guys up here have no water in them. This is when Mars died in terms of its water budget. So this boundary that we seem to be going across through the later history of Mars is possibly when it lost its atmosphere. We don't know that yet, but that's a hypothesis we're exploring. Okay, so with that as a background, let me just finish by saying that all over Mars, it just so happens to be that Gale Crater is the site with what looks like the most complete record. Because you've got green, at least some green. It turned out this is actually out of date. We've discovered a lot of green. There's a lot of clays down here. Then we go into the sulfates, and then we have all the dry stuff up here, all in one mountain. So let me tell you more about that mountain. So Gale Crater turns out to be a big impact basin where a meteorite struck the surface of the planet, and it did it in a place that we call the dichotomy boundary. And what is dichotomous about that boundary is that it has southern highlands, so the hotter colors are higher elevation, and the blues and the purples are lower elevation, and the white colors are the lowest elevations of all. So this meteorite hits this boundary, and so there's a southern rim to the crater, a northern rim to the crater, and a mountain in the middle, and a moat that runs around it. And that moat may have been filled with water, because what we can see is our good old, ever since the Mariner days, channels cutting across the surface of the planet, and this one in particular, these guys look like they're all running down into this basin. So it's completely reasonable to propose that if the rover goes there, it might find evidence for ancient water really quickly, and then we can get on with the chemical characterization. But what is this mountain in the middle? So this is kind of a fun progression of craters on Mars that are very different than the craters on the moon, because these are filled. And so you can start down here, and you see the vestige of an ancient big crater, mostly filled. Then they're getting eroded away, and then you come up here, and then the one we're at is the one that is most eroded away. So this mountain in the middle was not formed by plate tectonics and mountain building, how we know on Earth. It seems to have been formed by the crater filling up with material, and then the wind eroding it away and blowing this stuff away. It seems hard to believe, but that's our favorite idea. Okay, so Gale Crater does have the thickest stratigraphic section on Mars that has all these different interesting mineral eras. This is our landing ellipse. So Curiosity landed right about here back in 2012. And what we want to do is land and then quickly drive over to this mountain to look at what's down at the bottom here that intrigued us so much from orbit. But the reason we want to do the layers is I really want to drive this point home, is that sedimentary rocks are records of environmental change. So when you go to the Grand Canyon and you look over the edge and you look down in the bottom, you see red rocks down here. Then they go into gray rocks. And then there's a truncation, just like we saw on Mars and at Siccar Point, where these layers come along and they're all truncated beneath these layers. So we know these rocks are older than these rocks. And then we go up and we see lots of red layers. That's what this stuff is in the foreground. And then at the top, we have other kind of layers. And you can go through this and see the evolution of life on Earth as you walk up through the canyon, represented by the fossils that are there. Okay, so what we want to do is explore this record on Mars. So these are the ships of exploration that were sent to rove Mars. You start out down here in the beginning with the Sojourner rover that landed in 1997. This was the first time that NASA returns to the surface of Mars after that 20-year hiatus because of Viking saying we didn't find anything interesting. Congress said, great, we're going to send the money elsewhere. So they finally got a budget back, but the idea was if these geologists are going to explore ancient rocks, they need to be able to move around, just like geologists walk around the Earth. So instead of a lander, you want to build a rover. And so this was basically what's called a technology demonstration, which is important because it means if it doesn't work, you can't call it mission failure. That's important for the relationship between NASA and Congress. But what you've got here, and you see this shared in common with all of them, is a 6-wheel drive rocker bogie suspension that's built so that it can drive over obstacles as big as the wheels, but without the deck being tilted, because the deck is where the solar panels are that harvest the energy from the sun so that the rover can do its thing. And if it tilts away from the sun, that's not a good thing. So that worked. That technology demonstration worked. We didn't find any evidence of water because we sent it to the only place that was safe enough, which didn't have anything of geological interest really, but it was a great place to do this tech demo. And so then we go ahead in the next decade and we build 2 rovers, Spirit and Opportunity, because at the time that Sojourner landed, NASA was still like 30% chance of success. So most anything you send is going to crash and burn. So they built 2 of them to help retire that risk, hoping that at least one of them would work. Opportunity is still going after 14 years. It was built to last 3 months and drive 300 meters. It's now gone almost 50 kilometers over 14 years. So obviously this is a good design. Let's just scale it up and make a bigger thing. But we had to go bigger with Curiosity because you have a lot of onboard laboratories, because we need to get the rocks and analyze their chemistry to understand if there were materials that microbes could harvest for metabolism. So inside here, there's a lot of sophisticated stuff I'll explain in a minute. And then in the back, instead of solar panels, this rover has nuclear power. It basically generates heat due to the decay of plutonium-238. That heat is captured by a thermocouple, and it generates electricity. And it generates approximately 100 watts. So that's like the light bulb in your refrigerator. And 100 watts per hour powers everything on the rover. Okay, here's some fun stuff. Why does this work for NASA? Because suddenly it's not 30% anymore. It seems to be working really well. And the mantra for the engineers at JPL is just like the old real estate saying, location, location, location. So in this case, it's test as you fly, fly as you test. So we don't build anything that can't be rigorously tested. And we don't ever do anything on Mars that we can't test first that's new. So if you operate within those conservative barriers, you do pretty well. So what this engineer is doing right here is a test of the thermal structure of the rover. So at the end of the wand, there's a little temperature sensor, and the engineer is touching the surface of the rover, which is being illuminated by a light source which emits the same energy that the sun does on Mars. And so all these rovers are built numerically, and they make predictions about what the thermal behavior will be. And thermal behavior is really important for these spacecrafts because all that metal will shrink a lot on the surface of Mars. You get 100 degrees centigrade variation in the temperature every day that Curiosity operates. And all that metal is expanding and contracting. So you better understand dynamically what's stretching and what isn't relative to the way that you predicted it would be. So this is the last major test of the rover before we box her up and send it off to Cape Canaveral. It goes in this Atlas 541 rocket, which launched in 2011. The day after Thanksgiving, everybody was shopping and we were launching rockets. Okay, so what I want to do now is show a video, but I think since I crashed, I'm just going to have to reload it by hand. Yep. I'll tell you a little bit about this video while I load it up here. This video was made by a guy who worked for NASA for 25 years, and he was told to not do anything dramatic. And he comes in one day with this video. Let me just find the right folder here. Movies, great. Okay. And he comes in with this thing where he's interviewed all of the lead engineers and something that just exaggerated the tension of the moment. And so in the context of this, NASA eventually screened this and didn't want us to release it. So I had to fly out to headquarters and convince them that it was in the best interest of public outreach to do this. Because what you're showing is the soft underbelly that we all are worried about. And if it goes wrong, NASA's going to get killed anyway. And if it goes right, all these engineers are going to look like heroes. So here you go.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off. And then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divergent maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Okay, so it worked. All those guys go off and have a big party, and then suddenly it becomes my 7 months of terror to deliver on the science. Some cool pictures that I'll show just because they are amazing. In the discussion with the chief engineer for bits of information to send back to Earth when the rover first lands, almost all of it's going to be engineering data that tells you rover state of health. And the beeps that the engineers hear that are telling them that everything is working, it's not really going to work for the public to say that we landed on Mars. So the picture you see on the left here is what I won in that debate, which is a single grayscale image of the picture of one of the wheels that you can see dimly through the dust-covered dust covers that were installed in front of the camera lenses so that you can see later. And in the background, we thought we could see Mount Sharp. That's all the data we get. Earth sets on the horizon. We have no more communication for 39 minutes, and then an orbiter goes overhead, and now we get a data relay that way. So the picture that you see on the right, the shadow's a little bit longer by 39 minutes on Mars, and now we can see clearly the mountain that we set out to drive to. So those engineers go off and have a great party, and this is all the data we have. And I can tell you, the science team, it's like 10 o'clock at night, we're on Mars time, which means we have to follow the Mars day. Every day on Earth, we go 39 minutes ahead. And, but we spent hours talking about these two pictures. But then we did go to bed, and we woke up in the morning, and here's what we saw. The taxpayers were engaging, you know. We were really worried about this because we'd done rovers before and they were small and cute. This thing's not small and cute, it's an SUV. And, but what we had missed in the last decade since Spirit and Opportunity landed was social media. So that video that you saw went viral. It crashed all the servers at JPL. It was hit hundreds of millions of times. And suddenly everybody had to know about this mission. And so it's great to then have the public attention, except, now you need to find something. So we got some data down. I'll just show some pictures quickly. We were all looking forward to the mountain, but we forgot in our excitement about the mountain in the middle that the mountain around the rim is its own substantial mountain range. And what's amazing about this picture, to those of us that live in LA, and you drive to Las Vegas, and you look at the basin and range, and this looks really similar. There's even some LA smog coming in. But that's dust on Mars. And then finally, we did get the data down for the view of Mount Sharp, and it's just breathtaking. You go out the Four Corners area and go to your favorite park, and you pay big money to go to this on Earth. We paid a lot of money to see it on Mars. But what was exciting about this is that what we were pretty confident was there from orbit now really shows up on the ground, and it's these layers. This is our book that we're going to read. We just have to get over there and start reading it. And what we're going to read is the history of these layers, and there's colors here that correspond to these materials over here. And all you have to know is that anything with a color in here was formed in water. So we just have to get over there. And what you can see is that we landed here at Bradbury Landing, and I had told the NASA administrator that we were just going to start driving, because this was called a go-to landing site. Land in a flat place that should be boring and then get on with it. And instead, what we do is we kind of drive in the opposite direction to some place called Yellowknife Bay, and now I'm going to tell you why we did that. So here's our landing ellipse. There's where Curiosity landed, slightly off center, and right next to it is a geologic feature called an alluvial fan, which is where we have evidence of water flowing out of the mountains and then down across this plain. And topographically, the purples are lower elevation than these colors, so we know we're downhill. So this sounds pretty good. Like, you know, if there was water there, maybe we'd get some. Here's another weird thing. This is a strange geophysical property called thermal inertia, and I'm just going to relay it to you. It's a fall day. Next time it's really clear day. Cold front comes through. You're walking downtown, and late in the afternoon you feel that building radiating heat to you. That's what you're seeing right here. This map is made during nighttime on Mars, and you look down with an instrument that measures the thermal energy being emitted by the surface of the planet. And notice all this red stuff. Well, you know, this red stuff is right in front of this alluvial fan. So we got the idea that maybe this red stuff is actually where there was water with minerals in it that precipitated it and bound all the sediment particles together, making a hard rock. So this one I'm just going to blow over quickly to make the point that, let me go back and just point out that where the rover landed is just 500 meters away to get to the red stuff. And then here's a geologic map that we made, and that place, we landed right here. And all you have to see is that there's green, red, and brown, and that's all I'm going to say, is if we drive over there, we're going to find a threefer. Okay, so we did. We drove over there. You know, you're not allowed to use meters when you're talking to certain groups of people. So it's like five football fields to get there. And we gave it a name called Glenelg, which is a palindrome, which reinforced to NASA headquarters that we're going and coming. And then we got there eventually, and this is what we saw. And now we're in Moab, Utah, where you get your mountain bike and go out for a great ride. You know, this just looks awesome. So we went down in there, and here's the rock that we see, and it looks like it's got a case of the measles, but it's also got these fractures in here that are filled up with a white mineral that we can analyze with our instrument. That mineral has got water and its chemical structure. So we drilled it. 7 centimeters deep is as far as we go, and this is what you get for $2.5 billion. So we built this drill to analyze these rocks that formed in water, and here's what we found. So a little bit of data here for you. And these are a list of mineral names for things that are formed in rocks like you'd find at Hawaii. They're not formed in water, they're formed by melting of the earth. And then over here is the rock that we drilled, and you can see that all these minerals are much less abundant. And then down here we have something that's very abundant called smectite. That's a clay mineral that can only form in the presence of water, and there's a lot of it here. So in the interest of time, since the computer crashed, I'm going to skip a few, but this was a big discovery, and it was one of our first papers submitted to Science that we had all this evidence for minerals that were formed in water. And I'm going to summarize by just talking about color. This is what 10 years and $2.5 billion gets you. When we landed with Opportunity in 2004, we had a tool that wasn't a drill, but we could scrape the surface of the rock. We know the planet is red today because the dust is anhydrous iron oxide. And we scraped the surface and we found out that the rock was also red, which isn't a good thing if you're a microorganism. You'd like to find some gray stuff. And that's what we did with Curiosity. So we have red Mars on the surface today, and then we drill gray Mars. And these red rocks that you see are like the sandstones that all the brownstones in Boston are made out of, New York City. They all come from the same red sandstone. And the sandstone is red because the iron in that rock is fully oxidized. But all the gray stones that you see that aren't such attractive building rocks, the iron is more reduced. So if you're a microorganism, you really like that because you can go both ways energetically. So again, I'm going to skip a couple here. And I'm going to just distill it to this. What we found was in 2004, we did find water, but we don't think it was habitable because it was too salty. So the reason that honey doesn't spoil on your shelf is because the water activity is so low. So you can pick up a jar of honey and say, look, we found water on Earth, woohoo. But it's not a habitable environment because a microorganism would die the minute it fell into it. What we found instead at Gale Crater was rocks that have the chemical energy that allow a microorganism to work like a battery, just the same way that batteries do on Earth. So all of this then, you wind up publishing your results in Science, and everybody gets excited. And if you want to hear about more details, I'd be happy to go into it. But thanks for listening.
So we have some time for questions, and following our tradition, we would like to begin with questions from students who are not yet in college. So high school, junior high school, elementary school, whatever. Preschool. Not yet. Surely there must be one. Well, what I'm going to do is allow old school questions and then, oh, good. Please. Repeat the question.
It's a great question. So the question was, are we only going to explore Mars, or are we going to do other planets as well? And the answer is other planets as well. There's a lot of interesting options out there. There's a mission that's going to launch in around 2020 to 2024 that will go to a moon of Jupiter called Europa. And this is an icy world, and the idea is that if you can get beneath the ice, you might find evidence of life living in the ocean there.
More school-age people, but not old school.
There we go. Okay, I think I heard, you guys were both answering at the same time, but somebody stopped. If humans go to Mars, could you find evidence of life faster? Is that the question? Yeah, yeah. It's a debate, because by the time you are able to get humans to Mars, a lot of time could pass by. We don't live in the economic and political climate that we did in the 50s and 60s, where we were racing against the Russians to make it to the moon and Mars. So without those big dollars, it's really hard to build a spacecraft that could actually responsibly send astronauts to Mars. NASA would like to do this, but unfortunately the dollars don't really allow it. So in the meantime, you've got rovers and robots, and everybody is now familiar with the use of drones. So they're going to be everywhere in your life, and we actually think you can do a lot of good with robotic systems. And so I think that's the best hope we have for the foreseeable future.
There was another question over there?
Yeah, so the question is, how do we know that microorganisms can't survive in stuff other than like honey? So, honey is just something that people learn through experience, just doesn't spoil because the water is so low. But there is a picture I skipped over, and this is a place in Spain called Rio Tinto, and the river is red because the pH is so low, it's pH 1, that iron is dissolved in the water, and it gives it a red color. It's dissolved in the fully oxidized state, which we normally don't see on Earth. And this is really acidic. Like if you went in there, your skin would dissolve, but there are microorganisms that can live in there. So NASA's strategy includes looking at what we call extreme environments because microorganisms can adapt to that.
Any on this side of the room? School-age children? There's a school-age right there.
Can I give more information on microorganisms working like batteries? Yeah, so there are many different types of microorganisms, and the ones that might be most familiar to you are the type that use sunlight as a form of energy, but then there's another group of microorganisms that can actually live based on chemical energy. So if you have something like iron, and iron comes in the +2 state and the +3 state, the microorganism can take something that's in the +2 state and actually oxidize it to the +3 state and obtain that energy from the electron transfer that occurs.
Our time is limited, so I'll take some old school questions now. Right there, right here.
If you were driving around in the worst, sort of least life evident venue on Earth, how would what you would see compared to what you've seen on Mars?
Yeah, so the question is, if I was driving around if I can reword it a little bit, is there a place on Earth that looks like what we've seen on Mars? Is that fair?
The worst site on Mars on Earth for detecting life, how does it compare with what we've seen so far?
Oh, yeah, okay, that's a little bit different. So, it depends what you mean by the worst place for detecting life. Does that mean that environmentally it's not likely to support life, or I'm not allowed to have the right equipment to detect it? Yeah.
If you were in an old,
Yeah, yeah, no, got it now.
old site on
Yeah.
Earth that was very unpromising.
So, yeah, no, that's a good question. So Curiosity has no instrument at all that could detect life if it were there. If there were microorganisms in the soil and they were respiring, we would never know it. And so, NASA has a roadmap. And the first waypoint is build a rover that can drive around. The second one is find evidence of water. The third one is find evidence that that water could support life. And now we get on with the business of let's collect rocks to bring them back to look for life in our laboratories here on Earth. So 2020 is when that next rover launches.
Back there.
Yeah, every instrument comes with its own form of internal calibration, and in some cases, we can do cross-calibration with each other. So I'll just leave it at that. Yeah, there was a question right there.
Okay.
That's kind of my question, but how is this information transmitted back to
So it actually arrives at JPL, and there is a constellation of satellites distributed through the solar system, believe it or not, called the Deep Space Network. And we send information to those satellites, and then they relay the data back to one of three big 70-meter dish antennas that is either in Goldstone, California, Madrid, Spain, or Canberra, Australia, so that whenever data is arriving from the solar system, there's going to be a dish on Earth that can get it. And then it sends it back to JPL. Yes, yeah, speed of light.
There's a question here that's been waiting at the end. Yeah. No, back there.
What, if any, ground imaging techniques that we use, such as radar or anything terahertz range to image things which can't be drilled and show that it's 7 centimeters, but we're able to do that to do reflections, what would be this?
Yeah. So the 2020 rover that will do the drilling and return samples will actually have ground penetrating radar, but none have done that to date.
Back there.
I can't bet on something like that because I have no experiential basis to know how wrong I'm going to be. So I can say, sure, it'll happen. The problem is the experience I do have is we know the Earth teems with life, and we have enough of a fossil record to know that it's been that way since we get to the oldest well-preserved rocks on Earth. But yet when you go to those rocks, you almost never find evidence of life. You look and you look and you look and you bring rocks back to the lab and you're so hopeful you're going to find something, you get nothing. And that's because in the conversion of the sedimentary environment to the rock, there's enough mineralogic processes that are going on that the record of life gets erased. And so I think we're going to have to try over and over again. What I personally worry about is that the government will just lose its patience for this. If we don't hit pay dirt the first time, maybe we shouldn't try again. I mean, that's what happened with Viking. You get one negative result, now you lose 20 years. So I'm a big enthusiast for private and philanthropic enterprises who want to start doing cheap, low-cost missions of exploration to the solar system.
One here.
Thank you. You've mentioned the sample return. What do we hope to learn from sample return that the robot geologists cannot tell us?
Yeah, the very short answer to that question is if you get any rock sample and bring it to our labs on Earth, you're always going to do very much better with anything you could fly to another planet.
All the way back there.
I'm just curious your thoughts about the theory that's going around, the mountain that you spoke of tonight, that is an ancient pyramid, it has 4 sides, and it's directly center of that crater. Your thoughts on that?
Yeah, that's right up there with a grassy knoll.
It does have 4 sides, though, like a triangle, it's an ancient pyramid.
Yeah.
Center of the crater.
Yeah. Well, at the center of every impact crater is something called the central peak, which is what happened when you get the big energetic energy transfer. It bounces some of the energy back, and you get a peak. The thing is that Gale's not really, it's actually not really a pyramid if you look at the topographic data. It looks more like the wing of a bat.
We have just a little bit more. Right here.
Now that you found the minerals in the rock that were formed by water, what are the next steps forward for NASA on Mars?
Well, so when Spirit and Opportunity found evidence for ancient water, then we got the green light to build Curiosity to look at the chemistry of the water. And now that we find a favorable chemistry for the water, we get the green light to build the rover to collect the samples to bring them back. Because that's the best way to look for life, is to analyze them with all our equipment here on Earth at places like MIT.
When we bring the samples back, what steps do we take to avoid contamination?
Great question. With sample return, how do you avoid contamination? So that's the most expensive part of that mission, is making sure that we don't forward contaminate Mars. And there will obviously be a period where the samples will be held in a place until we can believe that there's not Martian life there. But honestly, what we're mostly worried about is forward contamination from Earth and then bringing that contamination back again and getting a false positive for life on Mars by finding something that comes from Earth.
All the way back there in the middle.
Yeah, it's a great question about, how might you expect a microorganism to metabolize differently from Earth? So it's a little backward thinking on our part to just assume that microorganisms on Mars would have evolved the way that life did on Earth, but that is the only paradigm that we have. And so I really subscribe to the notion that we must exhaust that search until you move on to something else like silicon-based life instead of carbon-based life. But these other planetary systems that NASA wants to go to, that might actually be a good starting assumption for planets like Titan. There's liquid hydrocarbon there, but maybe there's other types of microorganisms that would form.
Time for one more. I'm going to go all the way in the back. There.
You mean if we couldn't have made it to Gale, would there be another place to go to? Yeah, NASA carries forward all the landing sites for every mission because they always remain attractive to the science community. So the place that so next week, that mission will choose its landing site, by the way. And the options that they have are really good because they're going to fill out the suite of different diverse terrains that exist on Mars that might present different types of environmental histories.
So unfortunately, we have to stop. So let's thank John again. And also, if you'd like any information on the Lorenz Center or the Department of Earth, Atmospheric and Planetary Sciences at MIT, you can speak to us or stop by our website. So thank you very much for coming.